start with Samson Abramsky, and we'll be talking about unifying principles for Bell inequalities.
Thanks very much. Okay, so thanks everyone for turning up on first thing in the morning for a long way into this conference. So this is joint work with Lucy and Harvey. The topic of Bell inequalities has been there's such an enormous literature on it that one might feel there wasn't much left to say about Bell inequalities, but it seems to me that if one asks what is a Bell inequality, what's the sort of a clear conceptual unifying principle, then I'm not so sure there is a crisp answer. Maybe you feel there is one I'd be interested to hear, but it seems to me not so clear from this enormous literature. So what we're going to do is to introduce a form of Bell inequality based on logical consistency conditions, which we therefore call logical Bell inequalities. And we show that in some sense this notion is everywhere in studying Bell inequalities, because in fact one could show that a rational inequality is satisfied by all non-contextual models if and only if it's equivalent to a logical Bell inequality. And that says that quantitative tests for contextuality or non-locality always hinge, if you look at it in the right way, as it were, on purely logical consistency conditions. And I think this is something worth being aware of. In fact, these results work at a high level of generality, so they apply to all the familiar cases of Bell-type scenarios for any number of parties, but also to things like Coach-and-Specker configurations, and in fact to any family of sets of compatible measurements. We get this generality by working with measurement covers following a sort of general unified approach to non-locality and contextuality using some sheaf ideas which appeared in a paper of mine with Adam Brandenburger last year. There won't be any sheaf theory overtly or anything like that in this talk, but those ideas will be in the background. And in fact, there's a lot of interesting special cases where I think perhaps these ideas may be most useful. For example, there's a notion of strong contextuality which has emerged in the work I was just mentioning, and which comes up in a lot of places once one starts looking for it. One can show quite directly that the model achieves maximal violation of a logical Bell inequality exactly if it's strongly contextual. So it's another equivalence for this idea of strong contextuality. And there's an immediate application. All Coach-and-Specker configurations lead to maximal violations of logical Bell inequalities in a state-independent fashion. And we can also get specific violations of logical Bell inequalities for models which admit proofs of contextuality or non-locality without any use of inequalities or in fact of probabilities, essentially those which are susceptible to the Hardy argument. Since Lucy isn't here, I can use expressions like the Hardy argument, because most particular about removing all such things from the paper. So there is a paper about this which is available on the archive, and it builds on two previous pieces of work. A beautiful paper by Lucian from, I think one of the very first papers he published, which is a bit less well known than a couple of papers he published a year or two after that, but contains the sort of seed of the idea applied in a particular case. And then, as I was saying, the general setting fits nicely into this picture in the paper with Adam Brandenburger, which appeared in last year. Okay, so let's begin from scratch, just with a simple sort of thought experiment, just a simple exercise in logic and probability. So we suppose we have formulas of propositions. So by the way, I hope that everyone is happy with the idea of formulas of propositional calculus, so expressions built up from logical variables, Boolean variables by and or not, and similar things. So suppose we're given n of these, and suppose that we can assign so we can think of these as describing events in some Boolean algebra, of course. So suppose we can assign a probability pi to each formula phi I among these. And the story that we can tell, or particularly interested in telling, is that these variables that appear in the formulas are the sort of 0, 1 quantities, so we can perform some experiment to test them or measure them. We can perform and so each formula expresses a condition on the outcomes of such an experiment. And the experiments can be repeated, so we get relative frequencies, and therefore we attach probabilities to these formulas. That's the story, but of course it's quite general. The little derivation will now embark. So now let's form the conjunction of these propositions, which I call capital Phi, and let capital P be its probability. So now we do a little derivation that we might very well have as an exercise in week 2 of probability 101, which is we do a little calculation like this. The complementary event, you can see every step is very simple. This could be a class exercise, and we tidy it up a bit, whoops, and we get that the sum of these probabilities is less than or equal to n minus 1 plus p. N is the number of formulas, p is the probability of the conjunction. Of course, the algebraic maximum of this sum is n, because these are probabilities, so they can be at most 1. Well, now I give you an extra piece of information. I tell you that these formulas are jointly contradictory. In other words, their conjunction is unsatisfiable. So it describes the null event. Since it describes the null event, its probability must be 0. And therefore the inequality simplifies to the sum of the pi being less than or equal to n minus 1. Okay, nothing to see here. Very trivial. But quantum mechanics tells us that we can find propositions describing outcomes of certain measurements, which have been performed, and we get very highly confirmed probabilities for these experiments. And the propositions are easily seen to be jointly contradictory, and nevertheless this little inequality that we derive is observed to be strongly violated. In fact, the maximum violation of 1 can be achieved. So, a nice question, how can this be? So, if I was introducing people to some of the conceptual and features of quantum mechanics, this would be a nice point to discuss. Since I'm in a room with experts, I'll just let you identify for yourselves which step in my elementary reasoning from the previous slide we would have to give up in connection with quantum mechanics. A very innocent looking step. I guess it's clear enough to once one's been exposed to these things. But we can come back to it later. Anyway, an inequality of this form. So we have some formulas whose conjunction is unsatisfiable. So we can write a formal expression like this and say that their sum is below n minus 1 is what we call a logical Bell inequality. We'll generalize it a little bit later, but this is the basic form that we have in mind. Okay. So now let's apply it to something much more familiar in the quantum context. So here is a familiar table, I guess. So it's the usual kind of scenario. Alice has measurement settings A and A prime. Bob has measurement settings B and B prime. There are outcomes 0 and 1. And we can perform experiments and get statistics, and we get this particular bunch of numbers. And of course, in quantum terms, this can be realized by a Bell state with measurements in the XY plane at 60-degree angle to each other. So this is a real table arising from experience. So a good question, I think Tony Assin was sort of discussing this in his talk a couple of days ago, is you look at a table of numbers like this, we want them to speak to us. What structure can we discern that will tell us whether something non-classical is going on? So here's how this idea can be applied in this familiar case. So if you think about this table, even before we write the numbers in, a cell in this table is already describing an event. So the position here is the event where Alice did measurement setting A and observed outcome 0, Bob did measurement setting B and observed outcome 0 also. And in general, all of these cells describe such events. And we can think of those events as possible values that these these measurements can receive. So we're going to treat the measurement settings as logical variables, which can be assigned 0 or 1. And on each row of this table, what I'm going to do is pick out two of the events in this case, pick out a subset of the events by writing a formula in these variables whose set of satisfying assignments is exactly the cells that I've coloured in yellow. So if I do that, we get the following formulas. So on the first three rows, we're taking obviously the correlated outcomes. So what that says in these terms is it's a condition in the variables that say they must receive the same truth value. And in logical terms, that's just the if and only if connection. And on the other hand, here we have the anti-correlated outcome, and that's the exclusive OR of these two. So it's easy to see this collection of formulas, the conjunction of these formulas is unsatisfiable. If we start from the last one, then we can use phi 3 to replace A prime by B. We can use this one to replace B by A. And we can use this one to replace A by B prime. And we end up with B prime exclusive of B prime, which is obviously unsatisfiable. So this conjunction of formulas is unsatisfiable. The little principle we had earlier immediately tells us that the sum of these probabilities should be less than or equal to n minus 1, n is 4, so it should be less than or equal to 3. And we see that that inequality is violated by a quarter. So a very familiar case falls out in this fashion. And in a sense also we can see that this gives a rationale for why we take this choice of, particular choice of correlation. Okay. Now let's go to a case where we can do something better than that. In the previous case, we had to find the right set of events, and then we had to look at the numbers and so on. When one speaks of a Hardy-type argument or a proof of Bell's theorem without inequalities or without probabilities, what one's really saying is you don't need any information about the probabilities to derive the theorem. But actually, you don't even need any information about probabilities to derive the inequality, and all that the probability does for you in the end is tell you the degree of violation of the inequality. And that's what we're going to show here. So this is a typical example of the Hardy construction. Sorry, Lucy, you're not here, I'm getting away with it. So we're going to, and what I'm showing you is not the probability table, but only the support of the probability table. So I simply put a 1 whenever there's a non-zero probability there. So again, we're looking at this table of 1s and 0s. What structure can we discern here to tell us something about whether non-locality is present? Again, what I'm going to do is pick out a subset of each row by writing an appropriate formula. But here there's a more systematic choice that's directly available to us that, as we'll see in a moment, will apply to any of a large class of scientific examples. That is, I choose one particular element in the first row here, and then on all the other rows, I take the full support. So the full support on all the other rows. And if you look at what the formulas are, this one we're picking out a unique element, so it's just a conjunction of A and B, and then you can see that these formulas describe the full support on the other rows. And again, it's easy to see that these formulas are not simultaneously satisfiable. From the first and the second, I can derive not B prime. From the first and the third, I can derive not A prime, and then I get a contradiction with the fourth. So that again immediately tells me that there must be, that we get an inequality less than or equal to 3 for the sum of these 4 events. But here I've got full support on all of these 3 rows, so that's accounting for 3. And therefore I know a priori, without you even showing me what the probabilities are, that I will get a violation of the inequality by the amount exactly of the probability of this event. So let's now be a little bit more general. So what we're looking at in these events, if we have some set of measurements, is assignments of possible outcomes, which we label as 0 and 1. And the general setting we're going to work in is we have some set of variables which we'll think of as Boolean variables, and a cover, which is a family of subsets whose union is the whole set. This is where we get the generality I was speaking of, because if you go back to an example like this, the sets we have in mind are A, B, A prime, B, A, B prime, and so on. But it could be that particular simple structure of a cover is just one special case of the situation. We define a probability model on a cover just to be a family of probability distributions for each set in the cover on the possible events with respect to that set. So that's exactly like saying that we have a probability distribution on each row of the table. And what is the significance of the cover? These are the compatible sets of measurements, so the ones we can perform together. And so therefore they define the rows of a table. If we give you such a row, the 2 to the u is a set of possible outcomes, and the distribution gives the probability for each such joint outcome. Of course, the support of the model is just those events which get positive probability in this model. Now here comes the sort of key notion for our purposes, or as much of it as we'll need here, which is the idea of a global section. Which here we just can take in the simple form of simply an assignment to all the variables simultaneously, whose restriction at each of these sets sits in the support. So it's a possible event according to the model. So it's a simultaneous assignment to all the variables of a definite value, whose restriction to each of the possible scenarios we can experimentally access by performing all those measurements is consistent with what the model tells us. Now, if we turn this into logic, this is just a truth value assignment to our bunch of logical variables. And to say that global sections, to say some assignment like this is a global section is exactly to say that it's a satisfying assignment of the formula we get by forming the conjunction of all of these formulas which characterize the support in each row of the table. And in some sense, the existence of global sections provides a canonical form for non-contextual hidden variable theories. There's a little bit more to it than that. The details are in that paper with Adam Brandberg that I was mentioning. And there's a geometric idea of this, that we're gluing together this local information that we get over these sets into some piece of global information which is consistent with all the local information. So the idea is geometrically that non-locality or contextuality arises obstructions to this possibility of gluing things together. Okay. So now let's come back to the Hardy argument and see how we can give a more general account of it. We can say that probabilistic, when I say possibilistically non-contextual, or admits a Hardy type argument, admits an argument without probabilities, that it is contextual or non-local. If for every element of its support, there's a global section which lives on the support, which is compatible with the support, and which restricts to that particular. So every piece of behavior that's possible according to the model could be accounted for by some global assignment to all the variables. And if that doesn't hold, the model is contextual. And this condition, this form of contextuality implies, and in fact is strictly stronger than, the usual notion of non-locality or contextuality. So for example, the Bell table that we started off with is non-local, but it's not non-local in this stronger sense. That's why it doesn't admit a Hardy type argument. But here this gives a general condition that picks out those things that do. And then the result that we get, which is just the general form of the particular argument we gave for the Hardy model we looked at earlier, is that any possibilistically contextual model which therefore by definition has some possible event in its support sitting somewhere with some combination of measurements, which cannot, as it were, be extended to a global section, will violate a Bell inequality by exactly the probability of that event. And the idea is exactly the one that we saw earlier. We pick a formula that just picks out that one event on that row. On every other row, we take the formula that describes the whole support. And the fact that we can't extend it in this way is exactly saying there's no satisfying assignment for that bunch of formulas. Then the logical Bell inequality argument holds, we should get an n minus 1 bound, and in fact it's exceeded exactly by the probability of this event. Okay. Let's take another example. The W's say, which also admits a Hardy argument. And again, we just focus on the support table. We don't need to put in the probabilities. And we just look at the relevant rows for the argument. So we're measuring, the two choices of measurements are X and Z measurements, respectively. And firstly, we have the Z row, and we see the support there is just saying that 2 out of the 3 Z variables are true and the other is false. That leads directly from measuring this state in the Z basis. And then we have the 3 rows where there's 1 Z measurement and 2 X measurements. And you see, for example, if we take this one, then the possibilities that are excluded are those where Z gets outcome plus, and now we're reading plus as true. Z gets outcome plus, but the 2 X's get different values. So to exclude that, we exactly need the formula that says whenever the Z variable is true, the 2 X's get the same values. In other words, they're logically equivalent to each other. And we get 3 such formulas in a symmetric fashion that describe the support on these 3 rows. And now it's easy to see that from these formulas, well, if we start off with this one, we can argue by cases. So take the first case, where Z1 and Z2 are true. So then we can apply the first 2 of these formulas to say X2 is equivalent to X3, X1 is equivalent to X3, therefore all 3 are equivalent to each other. And in all the other cases, we can make a similar argument. And so we derive this formula here as a consequence of these 4, which is saying that logically then it can only happen consistently with what these 4 say, that the support lies in the first and last columns of this row. So everything else, and we see they're all 1s, so they're all contributing to a violation of the logical Bell inequality. So therefore, if we take again the formulas for the support here, and now we can sort of, to maximise the violation, we can take all the formulas in the complement of this theta. So that's all the 6 items here. Well, we should have a logical Bell inequality which is bounded by 4, and we're actually going to get a violation which, if we do fill in the probabilities in this case, is 0.25. Okay, so that was a general account of Hardy type arguments, which, as we've seen, are stronger than mere non-locality as manifested by the Bell table. But there is something stronger yet, which is this idea of strong contextuality. So a model is strongly contextual if its support has no global section. And that can be read in this logical language by saying the propositional formulas describing its support, the full support on each row, are not simultaneously satisfiable. There's no way of being consistent with all of them. That is a very strong condition. It's equivalent, for example, to being maximally contextual in the sense of having no non-trivial convex decomposition into a non-contextual model and a signaling model. By the way, I keep saying contextual rather or non-contextual rather than non-local or local, because we're working in this generalized framework with covers, which simultaneously includes both the usual discussions of locality and other manifestations of contextuality as well. And prominent examples of things which are strongly contextual and which live in quantum mechanics are the QISW states. Also, of course, things like PR boxes and so on that go beyond quantum mechanics are strongly contextual. And there is a strict hierarchy. The models we looked at just before, for example, the W state, which does admit a Hardy argument as we just saw, is not strongly contextual in this sense. So there's a strict hierarchy of properties of models, of which these are prominent examples. And in fact, we can see quite directly that a model achieves maximal violation of a logical Bell inequality if and only if it's strongly contextual. Because how are we going to get the algebraic maximum of the sum of the probabilities? Well, if we've got the full support in these things, every one of them gets probability 1, so they're going to go right up to n. And on the other hand, if we do get a maximal violation, we must be covering the support on some number of rows, and they're already inconsistent, so they're only going to get more inconsistent if we include more of those. So it's easy to see that these two things are equivalent. So again, strong contextuality emerges very naturally in relation to maximal violation. And just to give the example, we could look at QISW. Again, we just need to look at the relevant part of the support table. This is perhaps more familiar. I mean, we can write the support in terms of exclusive OR with negations in the appropriate places. And in fact, there was some discussion of the argument with instruction sets a couple of days ago. In fact, we can very clearly or easily understand instruction sets in this context as exactly truth value assignments. And the argument by Mermin in these terms simply amounts to saying that these formulas are not simultaneously satisfiable. Incidentally, there's a little quirk here, is that the argument is actually more laborious in the tripartite case than it is in all the higher cases. Once you go to 4 and above, you can make a simpler argument, which arises from the fact that the multiplicative group of I is arising naturally here and controlling things, so the 4 element cyclic group. But anyway, a certain amount of case analysis in this. Okay, so that's strong contextuality. Now, coming on to Cauchy-Specker configurations, the notion of model we're considering is actually much more general than the usual Bell scenario. Let me make this point. The Bell case arises in these covers from a very particular kind of case, by no means general. It arises when the observables are partitioned according to the sites of parties, and the sets in the cover correspond to a choice of one observable from each site, which we then represent on a tensor product in the standard fashion, so they all commute with each other. But that's a very special case, and for example, any Cauchy-Specker configuration gives rise to a cover in our sense. Given a family of unit vectors representing distinct rays in the usual fashion, we can build observables, and in the usual fashion, the observables will be compatible just if the corresponding rays are orthogonal. So the maximal compatible families correspond to the families of vectors which determine orthogonal bases. And that means that we get, the important point about this is that we get an a priori constraint on the supports of the models. We get an a priori constraint that the only possible outcomes, the only ones that can be in the support, are those where exactly one of the outcomes is labelled 0. If we follow that convention of labelling. And that means we can very easily give a logical description in these terms of Cauchy-Specker. So what we're saying is logically that the support for any model, for any quantum state whatsoever, given that you have this configuration of observables, must satisfy this logical constraint on each compatible family of measurements. This is just a formula that says exactly one is true and all the others are false. And then the essential property of Cauchy-Specker is exactly saying that there's no global section for this, there's no satisfying assignment for this conjunction. And it follows immediately then, that given a Cauchy-Specker configuration, the probability model generated by any quantum state is strongly contextual. Any quantum state at all is strongly contextual because it has to live inside here, and by what we've said, there will be no assignment at all in its support. And that, I think, fully explicates the state-independent nature of the theorem. And the obvious corollary you get then is that for any Cauchy-Specker configuration and for any quantum state, the corresponding model maximally violates the logical Bellin. So here's a little example, 18 vector configuration in R4. So we're going to have a cover with 9 sets in it. So the sets correspond to the columns here, the compatible families. The standard argument, using the parity argument, generalized in fact, says that, exactly that this formula is unsatisfiable. And for any quantum state then, the resulting probability model will maximally violate the canonical logical Bellin equality that just picks out the support of the model, or that actually this formula, that uses this formula to determine the logical Bellin equality, and it will be maximally violated by any quantum state. Okay, so now let's come to a more general picture of these logical Bellin equalities. We're going to generalize slightly, which we need to do to get something that is sort of universal for capturing contextuality and non-locality. So we're going to look not just at sets of formulas, but at multi-sets of formulas. So we write them as formal expressions like this, with non-negative integer coefficients. So in other words, formulas can appear with multiplicity. A sub-multiset is where you have fewer occurrences of a given formula, and the cardinality is just the sum of the multiplicities. So multisets are well used in computer science in many places. So we can then give an expanded notion of consistency for a multiset of formulas, actually even it's natural even for a family. We can say that such a multiset is K-consistent if for every sub-multiset of cardinality greater than K, the underlying set of formulas that live in that sub-multiset has no satisfying assignment. Actually, K-consistency is a very natural notion. For example, in computational complexity, there's a well-studied problem called MaxSat, which is the maximum number of satisfiable clauses in a given set, and there are weighted versions of that. So it's a very natural condition. So K-consistency is the notion that we're considering here. So our general version of an inequality is going to look like this. So we have formulas with possibly with some repetitions. And we have a general kind of bound K with a priori could be any positive integer. Doesn't want to be too big, but it's going to be interesting, of course. And so that's a formal expression we can write. And given a particular probability model, we can take these formal assignments of probabilities to these events and replace them by actual numbers, and then the inequality is satisfied by the model if, when we do that substitution, we actually get this inequality satisfied in this fashion. So here's the basic result, that this inequality is satisfied by all non-contextual models if and only if the multiset is K-consistent. So that's inherent in the idea of non-contextuality. And just, any non-contextual model can be written as a convex combination of deterministic ones. So it's then not difficult to see that. And this gives rise to our general form of Bellin equalities. So a general notion of logical Bellin equality over a cover is given by expressions of this form, where the multiset of formulas is K-consistent. So this is defined solely in terms of this combinatorial cover, this family of abstract family of what we think of as labels for compatible measurements, and a purely logical condition on the formulas. So it arises from logical considerations. And the generalization lets us get somewhat sharper inequalities than we would get in the form that we saw earlier. So we have, so the K may be maybe rather less than the sum of the multiplicities minus 1, and that lets us get sharper inequalities. Okay, so the usual considerations of forming polytopes of models generalize smoothly to this situation where we have these measurement covers. And just as it holds in the usual Bell case, it holds in generality, as one can show, and as all in the paper of Brandenburger, if a model is a convex combination of deterministic ones, which means that it's the convex hull of a particular set of models which we think of as vectors in a suitable high-dimensional space in a fashion. So the set of non-contextual probability vectors, that's the rows of the tables we were looking at laid end to end in a single big vector, is the convex hull of this set of vectors. And then that tells us that this is a rational polytope, and by general considerations, Fourier-Motzkin elimination, we can show that it's characterized by a finite set of rational inequalities. But the rational inequalities are defined by rational vectors and rational bounds. So I give you a finite list of inequalities, and now given any model, of course they're hard to compute. Worst case complexity is bad, but in principle we know that that is the case. So now here's our completeness result. A rational inequality is satisfied by all non-contextual models if and only if it's equivalent to a logical Bell quantity. Well, the point is we start off with a rational inequality, and it's actually, we can transform it into something of this form, which is equivalent in the sense of being satisfied by the same models. And then we use this result that tells us that such a thing will only have been satisfied if by all non-contextual models, if this K consistency condition is satisfied. It's bound on a number of things that could be simultaneously consistent. So you can give a blank vector of rational numbers and a rational inequality, but under the surface, if it is going to be satisfied by all the non-contextual models, this logical consistency condition is just below the surface. It's always there. And in fact, combining that with the fact that we can obtain the rational inequalities, we can, for any cover, we can in principle effectively get a finite set of logical Bell inequalities, which defines it. The same. How much time do I have left? I started slightly late, but
3 minutes.
Sorry?
3 minutes.
3 minutes. So this was all with probability. We're dealing directly with probabilities, which one can argue are closest to direct input. But at any rate, correlation inequalities are widely studied, and of course they fit into this framework. They're a particular case where we take formulas of a particular form. An important point to note, and Matty pointed this out to me, I hadn't realised this before, is that when we can always pass from a probability vector to the corresponding vector of expectations, but we of course lose information in that process, and actually there are known examples of highly non-contextual, non-local models which nevertheless, whose expectation values look like the expectation values of local models. Even extremal vertices of the no-signaling monotone, that can happen. So what we know is that we would be able to detect the non-locality with a logical Bell inequality, but when we have less information to deal with expectations, then obviously that won't be found. Nevertheless, it's of interest to show also that in a similar style we can give a characterization of the correlation inequalities, in other words of the polytope with expectation values. And this arises simply by taking formulas of a restrictive form. So in some sense we're taking a less expressive fragment of propositional logic and only taking the events that are definable in that less expressive fragment. and it's that which accounts for the sort of loss of ability to detect non-locality in some cases. And here's an example which I think is quite nice to illustrate, firstly, why we need this more general form of K-consistency, and secondly, how things that look as if they couldn't possibly have anything to do with a logical consistency condition, in fact do when you peer underneath the surface. So here is one of the correlation inequalities as tabulated by Werner and Wolff in the tripartite case. So here's how the inequality looks. These are expectation values. So there's no logic there, obviously. If we expand it out, then make it a bit more explicit, then we can follow exactly the transformation procedure that's sort of behind the results we just mentioned, which is quite straightforward, and we can convert it into a logical Bell inequality. Exactly the form we've been discussing. This is a nice example where this more general notion of K-consistency comes into play. The point is that all these 7 positive correlation formulas are consistent with each other. This is the nasty formula, the negative one. It's like, the sort of negative term in the CHSH. So this will blow up and give you an inconsistency as soon as you put it together with any 5 of the other formulas. So if we wouldn't be able to get at that fact if we were just relying on the simpler form of Bell inequality that we started off with. But now, because we count this one with multiplicity 3, then we can accommodate both the fact that all 7 of these can sit together and the fact that as soon as you put this with any 5 of the others, it will blow up because you can sort of buffer up 3 of them and still remain consistent. So we get a bound of 7, although there's a total cardinality of 10 in this multiset. Okay, so a couple of comments. We have been, it's convenient to focus on dichotomic measurements, but in the framework of covers that we've been considering, where we can have compatible families of measurements, this is not much of a restriction. Because we can use compatible families of dichotomic measurements, which all sit, if you like, at one site, if we have a sort of Bell-type scenario, to represent measurements with 2 to the p outcomes. It's not very restrictive. And there are some ideas about how some of these ideas can be adapted to the quantum set. And if you are curious to see any further details, there is this paper on the archive. So I hope you all have your own clear answer to the little puzzle we started off with, and I'll stop there. Thanks very much.
Thank you. Other questions? Yes.
So the hierarchy from the Bell is lower than Hardy, is lower than the strongly
Yes.
That's not a state-dependent classification, right?
Well, it's a statement about models which arise by taking arise in a quantum sense by taking a state and some choice of observables.
So, but if I have a state which satisfies 2 models in that, so how?
Yeah. So of course we would say, that's a very interesting point, which I was sort of talking about this. I think potentially there's a very interesting point about understanding the. This could lead back to looking at things like entanglement classes and so on, because GHZ states are certainly strongly contextual. There may well be larger classes of things that live in that vicinity. On the other hand, the W state, certainly with what seems like the right choice of observables to expose its non-locality, is not strongly contextual. As we saw, it admits a Hardy argument. It's in the middle of that hierarchy, but it's not strongly contextual. I would guess that it isn't for any choice of observables. I've shown that here. So that would be one way of getting at the difference between W states and GHZ states.
So I have one remark and one question. The remark is regarding a book by Itamar Pitowski. I don't know whether you're aware. I think the name is, the title is Quantum Logic and Quantum Probability.
Yes.
It goes far beyond your work, but so you're aware of this.
Oh yes.
Okay.
Yes. I
There are some
mentioned it in the.
instances of logical.
Sorry?
There are some instances of this logical.
Yes, but I mean so he particularly was kind of wrote about the connection with Bell's conditions of possible experience. But Bell's condition, sorry, not Bell's conditions, Boole's conditions of possible experience. So Boole to Bell, yes. So Boole's conditions of possible experience, indeed, yes, which is very interesting. Certainly, I think he's a seminal figure in this whole sort of literature, absolutely. But Boole's conditions are arithmetical in nature. So although it starts in a sense from logic, in Boole's time, I mean, the distinction between logic and arithmetic was not very clear in his work. And Boole's conditions are arithmetical in nature. We are focusing here on purely logical consistency conditions, so I think it's a rather different point, but I'm certainly aware of this.
Can you just perhaps shortly
go back to the...
to the second question you posed in the final remarks? Can you say something more about that? Maybe this idea to the quantum level, what you really mean with it?
Well, so there's a very clear picture that's emerged from this way of looking at things about contextuality being a matter of these obstructions to global sections. If we take, I mean, in the full probabilistic case, this amounts to getting a probability distribution on these deterministic non-contextual models. One result that we had in the paper with Adam Brandenberger is that if you allow negative probabilities in your probability distributions, you actually get all no signaling models. And negative probabilities are an idea that people have sort of flirted with, of course. People like Feynman and Wigner and so on. So that may be a sort of a negative remark about negative probabilities, but at any rate it shows that by having a more general notion of what a measure is on these non-contextual models, you may get more possibilities. So there's there's an idea that by having a more general notion of what a global section is, be more permissive as to what a global section is, we may be able to get a constraint that does cover the quantum set. So that's in general terms. I mean, I have one or two more specific ideas that we can discuss, but...
Okay, so let's play this together.